If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started. So now we are going to talk about a more practical approach towards data pre-processing or data preparation. And as you can see, the nodes are nicely separated. Probably we have more stuff to talk about here. Let's talk about the outlier treatment first. And you can see the nodes have been kind of shuffled. We are talking about the outlier treatment here first. You'll get to know why. First of all, if your data has genuine values, which seem to be very different from the others, outlier treatment is not applicable, period. We don't modify the data if the data is known to be good. We are not after any specific algorithms, assumptions that we want to definitely apply no matter how much data modification is needed. We probably would not even do an outlier treatment if the data is known to be good. Second approach, which might seem to be a bit of a shock for you, which is convert the outliers to missing values. Now, let's say there are cases where the outliers proportion in your data is very limited. Minuscule. When I say very limited, it's let's say less than 2 or 3% of the data contains outliers, and that too is not in a specific pattern, it's all random. In such cases, if you're going to modify the values, you may choose to convert the outlier values to missing values. And you'll get to know about how we do this in the hands-on pieces. But only in cases when the outliers are very limited is when you may choose to temporarily convert them to missing values. And of course, then you'll have to do the missing value treatment for them. Please note, once again emphasizing, we do not touch the outlier values if the values are known to be good. We would rather proceed with the outliers as is without modifying a lot of data. Next, we talk about feature scaling. Now, what are the approaches here? So if you see there's a color code that we have followed. If let's say there were outliers in the data and we have not treated the outliers, then this is the scaler that you want to use. So mostly we are taught about standard scaler and min-max scaler, which I told you in the earlier part, have a flaw. They depend on the outlier treatment to have happened, only then these are meaningful. But robust scaler is a median and interquartile range-based scaler, which does not require you to treat the outliers in advance. So you can use the robust scaler and proceed with the feature scaling. The other two techniques you already know. Now there is a dependency or there's a connection here, and then it comes to missing value treatment. Why are we saying that? So for missing value treatment, we recommend using an imputer. It could be a KNN imputer or an iterative imputer. These are readily available in the scikit-learn library. But why are we recommending these and not recommending the mean and median? Please understand the mean and median based approaches assume that each column exists independently. But when you have data collected around a context, most likely the features would have some or the other connection. We've explained this in our theory video on missing value treatment. But this KNN imputer, what it does is it looks at the entirety of the record, then finds out the most appropriate neighbors and gets their average as the imputed value. Now, why this color code is being used here is because this KNN imputer requires the data to be scaled before you perform it. So if you do a robust scaler, then you apply a KNN imputer, you're on the right path. Iterative imputer cannot be applied when your data has outliers. That's why we have marked it in red. It's not a bad technique. If you do not have outliers in your data, you can proceed with the iterative imputer as well. It's very powerful. But it is sensitive to the presence of outliers, and that's why you need to ensure that the data is outlier free before you apply iterative imputer. It's a regression-based technique, and regression models, as you know, are sensitive to the presence of outliers. Next, we have another dependency or connection between missing value treatment and feature selection. Now, if you notice, we used to have multi-collinearity here in the common approach, but we have changed it to feature selection. Why feature selection? Because this is a very powerful module within the scikit-learn library. Now, you know, scikit-learn library is the backbone library for all machine learning. If scikit-learn provides you something which is supposed to help you with feature selection, it's definitely worth your time. So we'll talk about different approaches. The variance inflation factor is already available through the SciPy library. We've repeated it here because it's a valid technique. But this tries to eliminate the features which are correlated. Now, why it's marked in red here is because this variance inflation factor is again meaningless if you have outliers in your data. You should not be relying too much on variance inflation factor. Then what are the things that we can use? We have variance threshold. Let's not only talk about eliminating features based on correlations. What if a column in our data varies very less? If it hardly varies or it's almost constant, it'll never be a good predictor for anything. And carrying such columns forward is meaningless. So irrespective of whether we had outliers in our data or not, we can first check the columns which are constant and we can eliminate such features. Then we have these supervised techniques which help us do feature selection. Why these have not been marked in green is because some of these techniques are sensitive to the presence of outliers. So you may want to customize these techniques appropriately. Recursive feature elimination essentially fits a model and tries to eliminate the features based on the feature importances or coefficients. Now you have a choice here to choose the appropriate model and then apply it. Same goes for select from model and sequential feature selector. So recursive feature elimination, select k-best, select from model, and sequential feature selector, these all involve checking the dependence or association between the target column and the independent features. Some of these, like select k-best, would check the association between every single variable and the target that you're trying to predict, while some other would try to check the association between the dependent variable and all the features together. Now, these are the techniques that we are going to cover at depth with proper examples and real-world data sets so that you get a solid grip on data preparation, particularly from feature selection perspective. In real-world data sets, mostly you'll have a lot of features, and to begin with, you will have to decide how many features you want to carry forward. Now, why did we talk about the connection between missing value treatment and feature selection? Because these supervised approaches would need the data to be complete. So you have to treat the missing values first, and then you can come to these approaches. Next, let's move to feature encoding. And when it comes to feature encoding, we just talked about label encoding and one-hot encoding in the common approaches, but there are times when you have data in a specific order. For example, good, average, and poor, these ratings, you should not do one-hot encoding. Why? Because they have an order. If you do one-hot encoding, you're losing information. So in such cases, when the categorical variable carries an order, you can do an ordinal encoding. If, let's say, you have 3 categories, you can encode them as 0, 1, and 2. Now, there could be times when you don't want to go ahead with the order in a linear fashion. You're saying that the lowest category I want to rate as 1, the category next to it I want to rate it as 5, and the category after that I want to rate it as 10. In such cases, you can actually do a custom encoding. And lastly, you may have such categorical variables which come with too many levels. In such cases, you can also do a target encoding. So target encoding is a very special encoding which comes through the category encoders module, which allows you to handle such categorical variables as well, which have too many values, too many categories. One-hot encoding is not recommended in such cases because it'll burst the number of columns that you have. And you may not necessarily be able to figure out the order in such cases when you have about 40, 50, 60 categories. Target encoding comes to your rescue there as well. So here's a zoomed out view of whatever we've discussed as the advanced approaches so far. And I hope you get an idea about the kind of depth to which you're going to learn here.